So what I wanted to talk about today is logic gates because I've invented my own symbology for how to represent logic gates, and I think they're pretty cool. So what a logic gate is it's a unit which takes two inputs to determine its output. And the inputs and outputs are traditionally shown in zeros and ones and falses and trues. They're pretty interchangeable, so I might use them interchangeably. So here are all the possible arrangements of inputs we could have. We could have either 0 and 0, 1 and 0, 0 and 1, or 1 and 1. Now, in the case of 1 and 0 and 1, there's a total of one true output in either case. And it would be weird if we treated one case differently than the other. So I'm going to treat these two cases as one case from here on out because they both have a total of one true output. So if we arrange, if we made all the possible logic gates, so all the ways that we could determine the output from these given inputs. So, for example, uh, this AND gate here, when there are zero true inputs, it outputs a zero. When there is one true input, so either of these cases, it outputs a zero. But in the case where there are two true inputs, it outputs a one. So all of these cases here are all of the possible different arrangements that could result in a logic gate. So I wanted to talk about two cases really quickly, the ground and the power. So in the case of the ground, no matter what inputs you have in here, it's always outputting a zero. So if you're always getting a zero out of here, then there's no really real point into giving it inputs in the first place because it's just ignoring it and giving you the ground. So if this is the result, if you wanted a result of zero, then don't use a logic gate, just plug it into the ground. And similarly, if you're always outputting a 1, don't use a logic gate, just plug it into the power. So now that leaves us with 6 left. And what you'll notice with these 6 here is that it's either the case that it's got a single 1 in it, uh, or a single 0 in it. Like uh, this one, and that one. So what I've done is I've arranged the single ones such that this symbol here points to the one, because they're arranged in the same order they are here. So these symbols point to the one when they're going upwards, and on the bottom here they point to the 0 when going downwards. So let's take this one for example. If we put a 0 and a 0 in here, that'd be 0 input, so we would look at the left digit, and the left digit is telling us that it outputs a 0. And if we inputted either 1 or 2 true inputs, then we would get a 1 coming out of here. So what is really cool about this is that how it interacts with the NOT gate. And what the NOT gate is it's this special logic gate which only has a single input and a single output. So what it does is it makes it the opposite. So if you get a 0 in, you get a 1 out, and if you get a 1 in and then you get a 0 out. And it's typically represented by the symbol. So I want to ask, what happens if you put two of them in a row here? So if you put two of them in a row, then your 0 becomes a 1, and then the 1 becomes a 0. So it's effectively canceling itself out. So that's an interesting case that we want to keep in mind. So why I bring up the NOT gate here is because I want to ask, what happens if we put it at the end of one of these logic gates? So what happens is whatever the output is, it becomes the opposite. And because I have these ones pointing at the ones and these ones pointing at the zeros, it has the effect of flipping it across the horizontal axis, because this 0 becomes this 1 becomes this 0, this 1 becomes this 0, and vice versa. So, as a rule of thumb, you can always say that a logic gate with a NOT gate at the end is always the same logic gate flipped about the horizontal axis. So the ones on the top become the ones on the bottom, the ones on the bottom become the ones on the top. And similarly, if we have two inputs at the beginning, well, what's that do? So let's go example by example. So if we put two zeros in here, the 0 would become a 1, and the second 0 would become a 1 as well. So we went from having 0 true inputs to 2 true inputs. So we went from going from this, using this column, to using this column. And if we put two 1s in here, the first one would become 0, the second one would become 0, and then we would go from having 2 true inputs to 0 true inputs, so we would go from using this column to using this column. So there is a flip about the vertical axis. So let's see if that continues. If we use one true input on the top and or a 1 and a 0, then that becomes a 0 and a 1. So in either case, we're still using one true input. So in the general case, we can always say that using two NOT gates at the beginning is the equivalent of using the same logic gate rotated about the horizontal axis. So these left ones become the right ones and vice versa.